Hi, my name is Adriano. I'm a PhD student at Ghent University, and today we'll be presenting the work entitled Influence of Weld Porosity on Crack Growth Measurement in Single-Edge Notch Tension Testing. That was a numerical study. I worked in this research with my colleague Robert Depraetere, also a PhD student, and with my supervisors Professor Waele and Professor Hertelé. Structural integrity assessments in welded structures often requires parameters related to the material resistance to fracture. For thin welded structures, such as pipelines, pressure vessels, and offshore constructions, single-edge notch tension (SENT) has been used as a fracture mechanics test specimen. The reason for that is that this specimen has a geometry constraint similar to the one found in these structures, which enables to obtain more realistic fracture toughness values. In this plot, you can see that the geometry constraint in a SENT and in a pipe are similar, leading also to similar values of fracture toughness. The SENT specimen geometry has the shape of a rectangular bar with a notch in the middle. Suto Laboratory in Ghent University has a vast experience in SENT testing, and it is deeply involved in research, both numerical and experimental, devoted to optimize SENT testing methodologies. It is in this context that this research was performed. SENT tests are used to characterize the toughness behavior of a material. That is done by constructing a resistance curve. A resistance curve is basically represents a material's resistance to progressive crack extension. So, in one of the axes of the resistance curve, you have the crack growth. So, it is necessary to measure the crack growth along the test. And also, we have in the other axis, we have the crack drive force parameter, like CTOD or J. So, with respect to the crack growth, the most used techniques to measure are unloading compliance and direct current potential drop. In the case of a weld SENT specimen, the notch is introduced in a weld region. So, in this case, your specimen might contain some porosities formed during the welding procedure. And these porosities might have an influence on unloading compliance and direct current potential drop measurement. So in this work, we tackle the influence of pores on crack sizing performed by unloading compliance and direct current potential drop. This presentation is structured in the following way. First, the unloading compliance crack sizing technique will be discussed, followed by the direct current potential drop. Afterwards, the numerical models used to perform the unloading compliance and potential drop simulations in SENT specimens containing pores will be presented. And then the results and the conclusions will follow. Starting with the unloading compliance technique. In this technique, some elastic unloadings are performed during the test. The inverse slope of these unloadings, also known as the compliance, can be linked to crack size by using polynomial equations obtained by fitting numerical results. In this work, we will be using the polynomial equation and coefficients obtained by Shen. Now, speaking about the direct current potential drop. In this technique, a direct current is applied through the specimen. Potential drop measurements are performed by a voltmeter across the notch. In case of a dual probe DCPD technique, like the one represented here, a second potential drop measurement is performed away from the notch. Then, a normalized potential drop across the notch, divided by the reference potential drop, is correlated to crack size using the analytical equation proposed by Johnson. The two techniques discussed previously, unloading compliance and DCPD, were implemented in a finite element model. The software Abacus was used both to create the models and to perform the simulations. For the unloading compliance, mechanical simulations, linear elastic mechanical simulations were performed. As boundary conditions, one of the side of the specimen was fixed and in the other one a displacement was applied. Crack mouth opening displacement values were extracted from the simulations along with a reaction force. For the direct current potential drop, electrical simulations were performed. As boundary conditions, an input current was applied to the upper surface of a current pin and a current out was applied to the upper surface of a second current pin. As an output of the simulation, potential drop across the notch was extracted. As said previously, the aim of this research is to investigate the influence of porosities in the accuracy of unloading compliance and DCPD measurements. In order to do that, two types of porosity were investigated: distributed porosities, a set of pores, and a single pore. Pores with a spherical intended shape were generated by deleting elements located in a dense mesh region of the finite element model. This region is called floor block. The notch was also modeled by element deletion. Regarding the model dimensions, B and W equal to 15 mm were adopted, specimen length of 150 mm and a floor block length of 10 mm. A floor block contains elements of two different sizes: two layers of elements of 0.2 by 0.075 by 0.2 mm and cubic elements of 0.2 mm. The notch is generated by deleting elements from these two middle layers. As a result, a notch of 0.15 mm thickness is generated. X-ray images are a common method of detecting volumetric flaws in a weld. Therefore, most standards judge the acceptability of distributed porosities in a weld based on indications provided by radiographic images. A critical parameter used to define acceptance or not of distributed porosities is the projected area. This table summarizes the maximum projected area in percentage tolerated by several standards. Tolerated values range from 5 to 2%. Randomly distributed porosities were implemented in the simulation matrix, based on projected area values defined in the standards. Random porosity distributions were generated and simulated. The porosity distribution were created based on three projected area values: 5%, maximum value tolerated among the analyzed standards, and two superior values, 10% and 15%. Three porosity distributions were generated for each of the three projected area values adopted. Porosity distributions contain pores with a diameter of 1 mm, 0.5 and 1.5 mm. In addition, for each combination of reduction in projected area and pore diameter, 4 notch depths were simulated. A 4 mm notch, considered as the initial crack, is 0, and 3 superior values that would emulate crack growth, 6, 8, and 10 mm. The evaluation of unloading compliance and DCPD sizing measurements are performed with respect to these depth values. Crack growth values obtained using unloading compliance simulations combined with Shen's polynomial equation are represented in the y-axis of this plot. In the x-axis, the real crack growth is reported. Bounding limits of validity set by BS 8571, a standard devoted to SCNT testing, are also represented in the plot. All points fell inside the validity bounding limits defined by this standard. That implies that the influence that the simulated distributed porosities would have on unloading compliance is not critical. In this slide, it is presented crack growth values obtained using DCPD simulations combined with Johnson's equation. This plot is analogous to the plot presented in the previous slide. Once more, all points fell within the validity limits defined by BS 8571, implying that the simulated distributed porosities did not significantly affect the DCPD results. The second type of porosity analyzed in this work is the single pore. Standards also present a criterion regarding single pores. The critical parameter used to judge the acceptability of a single pore, in the case of spherical pores, is the diameter. This table summarizes the absolute pore size tolerated by several standards. The maximum tolerated size is defined by a fraction of the base metal thickness, T, or by a fixed absolute size, whichever value is lower. Spherical single pores were implemented in a simulation matrix. The diameter of the simulated pores was chosen based on the tolerated diameter presented in the standards. A diameter of 3.5 mm was selected. This pore size would be accepted by some standards. A total of 10 pores in 10 different locations were simulated. The position of these pores is depicted in this figure. All pores are located in the mid-plane with respect to the specimen thickness. Pores 1 to 6 and 10 are not touched by the notches used to emulate crack growth, which means that they wouldn't be visible on the fracture surface of the specimen, making their detection more difficult. Pores 7 to 9 are in the way of crack propagation emulated by the notches. Crack growth values obtained by unloading compliance simulations and DCPD for all the simulated single pores are presented in these two graphs. In the case of the unloading compliance results, all points are within the validity limits defined by BS 8571. For the case of DCPD results, 2 points fell outside the standard validity limits, and therefore, for these two cases, cracking extension measurements would be considered unqualified by this standard. The porosity simulation results show that the parameter that affects unloading compliance and DCPD results the most is the position of the pore with respect to the notch tip. In the case of DCPD, a pore close or touching the notch forces the current, represented in the left figure by white arrows, to flow underneath the pore, affecting the potential drop measured at the surface. In the case of unloading compliance simulations, figure in the right, a pore in the notch region that is highly stressed, affects the specimen stiffness and therefore unloading compliance measurements. The following can be concluded from this work. Pores can affect crack size measurements performed by unloading compliance and DCPD. In some simulated cases, single pore simulations, the measurement inaccuracy caused by porosity exceeded the acceptability limit set forth by BS 8571. Pores next to the crack tip have a more pronounced influence on DCPD and unloading compliance measurements. Research currently going on at Sutte laboratory aims to experimentally evaluate the hypotheses resulting from this numerical work. Thank you very much for your attention.